Today, we're going to go over the top 5 most commonly asked system design questions in FANG interviews. We'll explain the system requirements and go over how we can build a system for it, answering everything you'll need to in an interview. And to make sure that you ace every system design interview you ever have, we're also going to create a template that you can reuse and modify to answer any system design question. By the way, if you want to practice these questions yourself and read a more in-depth walkthrough, check out our website at systemdesignschool.io. The first question we are going to look at is probably the most popular question asked in interviews, which is to design a Twitter clone. A social media newsfeed like Twitter displays posts from people or pages that a user follows, prioritizing them based on engagement and recency. The system needs to scale to millions of users while providing real-time updates. So, before we dive into the architecture, let's first lay out the basic requirements. In a system like Twitter, we're dealing with a high volume of both reads and writes. Users are constantly posting tweets and interacting with content, which means the system needs to handle a lot of incoming data while also serving a large number of requests to read data. Both reads and writes should be very fast, and for writes, the way we're going to achieve this is using eventual consistency. Our goal is to design a system that can scale horizontally and handle the increasing load as the platform grows. Let's start with how we'll be handling the incoming writes. We'll begin by adding a write service. This service will be responsible for accepting all of the data submissions from users. In the context of Twitter, this is where tweets, retweets, or any other user-generated content would come in. The write service needs to do some basic validation, such as checking if the user is authenticated and ensuring that the tweet adheres to platform rules like character limits and content guidelines. This service should be stateless, meaning that each request can be processed independently without relying on previous interactions. The reason for this is that stateless services are much easier to scale horizontally, which is crucial for handling large-scale traffic. So, a user sends a tweet, the write service validates it, and then we prepare to handle that data. Now, we don't want the write service to communicate directly with a database because we need to decouple these components. Why? Well, if the write service tries to write directly to the database and the database becomes slow or overloaded, it would slow down the entire system. Instead, what we can do is introduce a message queue as an intermediary between the write service and the database. This message queue will temporarily hold the data as it's submitted by the write service. By using a queue, we allow the system to handle spikes in traffic gracefully, as the data is processed asynchronously. This way, the write service can remain fast and responsive, since it doesn't have to wait for the database to confirm the write. The queue can also add a layer of resilience because if the database goes down temporarily, the queue can store the messages and process them once the database is back online. So now, when the user submits a tweet, the write service simply puts the tweet in the message queue, and from there, we can handle it asynchronously. Next, we need a component to take messages from the queue and actually write them to the database. This is where the database updater comes into play. The database updater listens to the message queue, retrieves tweets or other content, and writes it directly into the database, which acts as the source of truth. By having this updater run separately from the write service, we're making the system more modular. This modularity is really important because it allows us to isolate potential failures. For instance, if there's an issue with writing to the database, it won't affect the write service directly and users can still submit their tweets. The database updater can also implement retries if, for some reason, it fails to write to the database on the first attempt. This gives the system a lot more resilience and ensures that data eventually makes its way to the database without any user-facing issues. Now that we've handled how to deal with writes using the write service, message queue, and database updater, let's move on to how we're going to handle reads. In a system like Twitter, reads far outnumber writes. Users are constantly viewing tweets, profiles, and timelines, so it's important that we serve this data as fast as possible. To start with this, we'll introduce a read service. This service will handle all user requests to read data, like fetching tweets, profiles, or timelines. The key point here is that we don't want the read service to hit the database every time, because that would cause unnecessarily loads and slow down the user experience. Instead, we need a way to serve reads quickly. Since reads are happening frequently and we need to be fast, we can't always afford to query the database, which is the source of truth. This is where caching comes into play. We are going to use a cache to store recently accessed data. When the read service is receiving a request, it will first check the cache. If the data is already in the cache, we can return it immediately, resulting in a very low latency response. If the data is not in the cache, only then do we query the database and retrieve it and update the cache for future requests. This technique significantly improves the performance of our read operations, which is critical for a system like Twitter where users are constantly refreshing their feeds and viewing profiles. Now, you might wonder how we keep the data in the cache consistent with the database. We are using a pattern called eventual consistency, which means that the cache doesn't need to be updated immediately when a write happens. Instead, the cache can be populated on reads and periodically invalidated or refreshed to ensure it doesn't get stale. In our case, as new tweets are submitted and processed by the database updater, the cache can either be updated in real time or lazily refreshed when the read service detects that the requested data is no longer valid. This balance between consistency and performance is important in large-scale systems. This system we've designed, involving reading from a cache and writing to a message queue, is actually used in almost all platforms with user interaction, or any platform where users both write and read content at high volume. In fact, it's so common, we actually recommend using this template as the starting point for answering any system design question interview. You can start with this template and build off of it for each specific application. This is just the high-level design, which is enough for this video. However, there are a lot more deep dive questions you will want to address, such as, how should the system generate a unique ID for each tweet? And how do we handle the celebrity problem, where an account with a large number of followers posts a tweet and potentially causes a surge in traffic? To see how these are handled, as well as a much more in-depth explanation of how to design Twitter for an interview, check out our website at systemdesignschool.io. Now that we've already walked through designing a scalable system for a social media newsfeed, we have a good template for how to handle high volumes of reads and writes. We're going to use these same core ideas to answer this next popular interview question, which is to design a messaging system like WhatsApp. In a messaging system, users need to send and receive messages in real time. Unlike a newsfeed, where there's a focus on serving content to large groups of users, a messaging system primarily deals with one-to-one or group conversations. We need to ensure low latency for message delivery, support a range of media types, and provide reliable delivery with status updates. This system must scale to millions of users and handle spikes in traffic while ensuring that no message gets lost. So, our main functional requirements are: how do we send messages? How do we store messages? How do we deliver messages in real time? And lastly, how do we handle reads? Let's begin with how do we send messages? We'll begin with the same write service concept from the previous design, but we'll call it the message service. This service will handle incoming messages from users, whether it's a one-to-one chat or a group chat. Here's the process. A user sends a message through the message service, which validates the message. The message service shouldn't write directly to the database because we need to keep the system fast and decoupled. Instead, we'll use the same message queue approach we saw in the newsfeed system. The message is pushed into a queue for asynchronous processing. Why a queue? Well, just like in the previous example, this decoupling allows the system to handle traffic spikes, ensures resilience, and keeps the message service responsive even under high load. Now, how do we store messages? From here, we can use a database updater, a concept we derived earlier, to pull messages from the queue and write them to the database. But unlike the newsfeed system where the focus was primarily on read optimization, messaging requires quick writes as well, which is why we'll likely be using a NoSQL database, which can handle high write throughput and scale horizontally. This database will not only store the message content, but also important metadata such as sender, recipient, timestamps, message status, and more. And for group chats, we'll need to store the list of recipients and track the delivery and read status for each individual recipient. Moving on to the next question, how do we deliver messages in real time? Now, this is where the messaging system differs significantly from the social media newsfeed. We need a real-time message delivery to give users this sense of immediacy. For this, we'll introduce a notification service. When the message is stored in the database, the notification service will notify the recipients in real time, either via WebSockets for online users or push notifications for offline users. WebSockets are a key technology here because they allow for two-way communication between the server and the client, which is perfect for real-time messaging. If the user is offline, the message can be stored and sent later when they reconnect. This service will also handle delivery and read receipts, updating the sender when their message has been delivered or read. This feature adds a lot of complexity, but for simple sake, we can actually use a similar approach to the cache mechanism from our previous template. Lastly, how will we handle retrieving messages? For reads, we can again use the read service model from our previous template. When a user opens a chat, we'll first check a cache for recently sent or received messages. If the message is in the cache, it is returned instantly, ensuring low latency reads. If it's not in the cache, we can query the database and update the cache for future requests. This is especially useful for users who frequently open and close chat windows or scroll past messages. The caching layer reduces the load on the database and ensures a faster user experience, which is critical in a messaging system. And there we have it. That's how you do the high-level design for a social media feed like WhatsApp. Now that we've already answered 2 questions, we have a good idea of how to use this template for handling high volumes of reads and writes. We are going to use the same core ideas to answer these next 3 questions, but we're going to move much quicker now that we know what the general system looks like and focus only on the additional complexities of each of these questions. For this next one, we are going to design a popular interview question, which is a URL shortening service like Bitly. A URL shortening service converts long URLs into short, easy-to-share links, and when someone accesses a short URL, they're redirected to the original long URL. Using the existing template, we'll be adding several key functionalities needed for this specific purpose, such as unique URL generation, caching for popular URLs, and redirect services. The main questions we'll need to answer are, how do we generate unique short URLs? How do we store and retrieve URLs efficiently? And lastly, how do we handle high availability and fault tolerance? Let's start with, how do we generate unique short URLs? We'll start by using our existing template and building off of it. In a regular interview, you would have to explain how you got here, but since we've already done it twice in this video, I think it's safe to say that you know how to do this. To generate short, unique URLs, we need to add a URL ID generation mechanism to our write service. This could involve base62 encoding or hashing techniques on an incrementing ID, creating unique compact representation of long URLs. In this enhanced write service, when a user submits a long URL to be shortened, the service will generate a short URL that is unique. This short URL, along with the original longer URL, are then pushed to the message queue for asynchronous processing, which keeps the write service responsive under high loads. Now, how do we store and retrieve URLs efficiently? The database updater component in our template will be responsible for taking short URLs and long URL pairs from the message queue and then storing them in the database. The database now acts as the main source of truth, holding mappings between short and long URLs. But how do we retrieve them quickly? Well, for this case, we are going to use this cache implementation. We'll cache only the most frequently accessed or hot URLs. This allows us to serve popular short URLs quickly without always needing to requery the database. As we've seen before, the read service will first check this cache. If the short URL is found in the cache, it returns the long URL instantly. Otherwise, the read service will query the database to retrieve the long URL. Lastly, how can we ensure high availability and fault tolerance? The template system already provides high availability and fault tolerance with our message queue, database updater, and cache. However, we can go a step further to fit the needs of a URL shortener by adding a replicated database and distributed cache. By distributing both the database and cache, we can handle large traffic spikes and ensure uptime, especially for highly popular URLs that get clicked frequently. We can also add an additional redirect service that will be used in the read path. This service takes the retrieved long URL and performs the HTTP redirection, sending users to their intended destination. This keeps URL resolution fast and reliable. And just like that, we've created a complete high-level design for a URL shortener service like Bitly. As you can see, once you get familiar with this template, it becomes very easy and quick to get to the high-level design. After this, we might want to explore some deep dives that go into how the URL ID generation works from a technical perspective. If you're interested in a full walkthrough of that, check out our website at systemdesignschool.io. Now, just like we did for the last question on URL shorteners, we are going to extend our same high-volume read-write template and answer this popular interview question: design a scalable file storage system like Dropbox. A file storage system allows users to upload, store, and sync files across multiple devices. It needs to be able to handle large files efficiently, ensure high availability, and enable secure access control. The main questions we have to answer with our high-level design are: how do we manage large files and sync across devices? How do we ensure high availability and durability? How do we handle access control and permissions? And lastly, how do we synchronize files across devices? Let's start with how do we manage large files and sync across devices? Once again, let's start with our template. Building on the write service in our template, we'll be adding a chunking mechanism. When a user uploads a file, the write service splits the file into smaller chunks using this chunking mechanism. This approach allows for efficient storage and retrieval, as only the updated chunks need to be modified during syncing, and large files can be processed in manageable segments. The write service pushes each chunk to the message queue for asynchronous processing. This keeps the write service responsive, even for very large files. Next, how do we ensure high availability and durability? For storage, we'll replace the standard database in the template with a distributed storage system that stores file chunks across multiple nodes. The database updater becomes a storage management updater that updates the placement and replication of file chunks in the storage system, ensuring they're always available even if some nodes go down. To make our frequently accessed files faster to retrieve, we'll also be using the cache for frequently accessed or frequently updated files. This way, popular files can be served quickly to users without querying the main storage repeatedly. Next, we want to figure out how we're going to handle access control and permissions. In addition to file storage, we need to manage metadata associated with each file, such as permissions, ownership, and version history. To achieve this, we'll be introducing a new service called the metadata service. The metadata service stores information about file ownership, permissions, and version history. This allows the system to verify access quickly, ensuring that only authorized users can view, edit, or share files. When a user attempts to access a file, the read service first checks both the cache and the metadata service to verify the permissions, and only if it's available does it return the file efficiently. Lastly, how do we synchronize files across devices? To sync files, we need to add some sort of sync service. This service keeps files up to date on all devices linked to a user's account. When a file is uploaded, modified, or deleted, the sync service notifies all other devices associated with the user, ensuring that they have the latest version of this file. As you can see, taking our base framework and adding new things on step by step has given us a pretty robust high-level system for designing a system like Dropbox. From here, you could go into deep dives on how to store the chunks of the files more effectively, how to sync more efficiently, and how to send real-time updates after syncs. Again, the answer to all of these and many more deep dives can be found on our solution page, link in the description. By this point, you know the drill. We're going to answer the last question in this video, which is another super common interview question: design a video streaming platform like Netflix. A video streaming system allows users to browse, watch, and receive recommendations for content. It must handle high-quality video delivery, personalized recommendations, and high availability, all while minimizing latency and buffering. The main questions we must answer are: how do we handle video uploads and encoding? How do we manage video storage and delivery? And how do we personalize recommendations for each user? Let's start with how do we handle video uploads and encoding? Again, we'll start with our base template that served us well so far. To handle video uploads though, we'll need to enhance and modify our existing flow. When a new movie or show is uploaded, the write service handles the file upload and the metadata collection. After a video is uploaded, it's sent to the message queue for asynchronous processing, allowing the write service to remain responsive. This is what we've already implemented many times this video. To expand on this, we'll need to add special handling for video type files, which we'll do with a content processor. The uploaded video is passed to the content processor, which encodes the video into different quality levels, like 720p and 1080p, to support adaptive streaming based on users' internet speeds. This processor also generates thumbnails, trailers, and optimized metadata for search and discovery. Next, how do we manage video storage and delivery? The video storage component is crucial for handling large volumes of video data and ensuring smooth playback for users. We currently have this indicated by our plain old database, but due to the large volume requirements, we'll want to switch over to a distributed video storage system. Once a video is processed, it is stored in this storage system. To reduce latency for users in different regions around the world, we'll be replicating this video content to a content delivery network, or a CDN. The CDN ensures that users can access videos from a geographically close server, minimizing buffering and improving playback speed. On top of this, to optimize frequently watched videos, we'll make use of the cache in our template by storing popular or commonly watched shows. This allows for fast retrieval without repeated CDN or storage calls, and is especially helpful for trending shows and movies. Lastly, how do we personalize recommendations for each user? Personalization is key for a Netflix-like system, so we'll need to introduce a recommendation engine. This engine analyzes user data such as watch history, ratings, and viewing patterns to generate personalized suggestions. It could use collaborative filtering, content-based filtering, or hybrid models to recommend similar titles based on users' preferences and behaviors. When a user logs in or completes a video, the recommendation engine suggests new content, helping to drive engagement. How you implement this is up to you, and is definitely something you'd want to go into during a deep dive. Other important deep dives include how bitrate streaming works, how the encoding process works, and how you would ensure high availability and fault tolerance. Thanks so much for watching this video. If you liked it and want to see more, make sure to subscribe to our channel and hit the notification bell to stay up to date. Also, check out our website at systemdesignschool.io for system design interview practice, complete with an AI auto grader. Thanks, and we'll see you all in the next video.